Hey, what's up, guys? This is Chung here again. Today, let's take a look at this problem here. Number 1066, camper's bikes number 2. Very interesting. It's a good problem, it's a media level. I think it's a good medium level problem. Okay, I think I have uploaded another videos regarding camper's bike number 1. Okay, so this one is like a little bit of variation comparing with the other one. So let's take a look. Okay, so you're given like a campus represented like a 2D grid here. There are like n workers and m bikes, where like n is smaller than m, which means it's guaranteed that each worker can be assigned to a bike. Okay, and we assign one unique bike to each worker so that the sum of the Manhattan distance between each worker and their assigned bike is minimized. So this is the formula to calculate the Manhattan distance between those 2 points. Basically, with given like this n number of workers and m numbers of bikes, it asks you to find the minimum sum of the workers and the bikes. Mm, yeah. And as you guys can see here, right? So the name and the workers and bikes, the constraint is only like within the 10. So which means, every time when you see like this one here, like see like this small number of here, I think you should always try to think of like a bit mask. Okay. And and as for this problem, right? So this is like another classic two list of problems. Basically, you have a list one here. Okay, a list one, and then you have a list two here. List two. And they ask you to find like the minimum like values, right? Basically to connect each one of those into the other. Okay. We have seen some other similar problems, but with this one, right? So since the bike, sorry, since the worker is smaller than the bikes, so which means when we define the DP here, right? So the DP here, and the first one is the index, right? So we can define the first one with index because we know with this index, it means that between 0 and index minus 1, uh, uh, for all the workers within this range, they have already been assigned to a bike. Okay, so that first one is index. The second one is, of course, is the mask. It's a mask of the assigned bikes, right? So because since we need to check we need to track which bike had been assigned. So instead of looping through the whole list, we should always try to use a mask. Okay, so it's much easier for us to basically to compare or to track like the status of each bike. Basically every time when you have a list and you want to track the list of the status, always try to think of a mask here. Okay. So and yeah, basically that's the DP function here, and then after that it's just like the backtracking, right? The backtracking it's not yeah, it's kind of like backtracking plus a DP. So first, let's do a top-down DP here. Okay. Basically, with this index and the mask here, we can uniquely identify a current state, right? Because at this moment, if the previously this many workers have been assigned to a bike, right, plus this mask, then we know, okay, this is a unique state. That's why we can use this one as a DP definition. Cool. Hmm. So first, I'm gonna define like a helper functions to give us the Manhattan distance, okay, between 2 points. So return ABS P10 minus P20 class ABS P11 minus P21. Okay, so that's that. And the next one is, our DP here, DP functions here, like the index and the mask. Okay, so as always, right? So our template, right? The template is this one, and if index mask, if the key is in the memorization, okay, then we simply return the memorizations, right, with this one, with the values for this key here, okay? And then let me try to finish the template first, okay? So that's always a good thing to finish the template so you can focus on the actual business logic there. So and the template is that we will return an answer here, and we'll define like a answer equal a value here, and then later on we'll just assign this answer to this like memorizations, right? In the end, we simply return the answer. Okay. So and regarding our problem, uh, regarding this for this problem, since we're asked to get the minimum values here, that's why we need to assign this, initialize this thing to a maximum size of value here, so that later on we can get a minimum value out of it. Okay. So, and all right, so that's that. And now it's the time for us to see from the current state how many other like different scenarios we can go from the current scenario. So basically, and the scenario we can go from here is that, I mean, based on this one here with the current worker here, right? And what are the other possible bikes we can assign to this worker, right? And remember, this mask records the assigned bike status so far, right? So in order to do that, we just need to do a range. We just need to loop through all the bikes here, okay? And we compare the bit value so that it can tell us if this bike has been assigned to a worker or not, right? So to do that, let's search the bike. Let me define a length of workers, maybe a length of workers here equals to length of workers, okay? And then we also need the bikes here, right? So the length of bike, so that we can loop through the bike. So now we have a let's do a worker here. So we have worker here. Worker equals to the current index, right? The workers and the index. That's our current worker, right? And then now we just need to loop through what are all the bikes that we can assign to the current worker. Okay, so I in range of the of B, right? That's the yeah, and so we just need to check if this ith index has been assigned, right? The ith bike has been assigned. So how can we do that, right? We just do a if you guys still remember, like how can we check the bit value, right? So we do a bit shift to the left by ith position, and we do end with the mask. Okay, if this one is equal to 0, then we know this bike has not been assigned to anyone. Okay, so for those who still don't know the speed manipulations here, I mean, I'll briefly give you like an explanation here. Basically, let's say for example the mask is 0 1 1 0 1 1 0, and if we want to check if this bit value is 1 or 0, how do we check that? Basically, we create like a we create a like a mask value by uh, by doing this one here, right? So basically, we're creating like this 1 0 0 1 0 0 0 0. That's this like the bit shift here. By creating this one, and we do an AND with the original mask here, since every other bit value is 0. So the final result it depends on the end for this is 1 here. Okay, which means if the original mask, if the bit value of the original mask is 1, then the total answer, the final answer is this one, is 0, 0, 1, 0, 0, 0, 0, which is not equals to 0. Otherwise, if this one equals to 0, then it means the final result is 0. Okay, that's how we use this thing to check if the current bit value is 1 or not. Okay, so basically, if this one is 1, right? So, and we can get, so now it means that, okay, so we can assign this bike to the current worker. And now we can calculate the Manhattan distance between those two, right? So bikes I, right? So now we have a distance, right? Distance equal to get distance of the worker and the bike. Okay. Now we can do our DP here, right? So minimum answer of the what? Of the DP, since the bike has already been assigned, right? So now let's move to the next one. Okay, and we also need to update the mask. So to update the mask, which means to mark this index of bike to be 1. So the way we're doing it is similar like the how we check the value here. Instead of and, we just need to do a or here. Okay. Or the mask. Okay. Then this is how we set this thing to value to 1 here. And since we are like we didn't change the mask, we just directly passing like updated another value in here so that we don't have to do a backtracking. Okay, cool. So that's that. And sorry. So here we return the DP, right? 0 and 0. So because at the beginning we have 0 bikes and we have 0 0 bike and 0 worker here. So yeah, now the base case, right? Always remember to set your base case. So what is the base case? The base case is when the index is equal to the workers, which means when every worker has a bike assigned, then we simply return what? We return 0 here. Makes sense, right? Because sorry, because here, okay, I forgot to add this distance here. Because in the end, right, for the last workers, right, so for the last worker, after the last worker has been assigned to the bike, and then we do another like index plus 1 here, and then later we need to set 0 because there's nothing to be assigned here, which means in this case there's 0 Manhattan distance for us. That's why we just return the 0 here. Cool. I think that should work. Yeah, that's pretty much everything. Let's try to run the code here. Cool. So this one accepted. Let's try to submit it. Yep. So it's a success. I mean, yeah. I mean, for me, I mean, the top down is I think is more intuitive for me. So basically we're following the problem, right? Basically, the first we're assigning the bike to the first workers, and then we try all the possible bikes, okay, and then we assign the second one with all the remaining bikes, the third one, so on and so forth, until in the end we reach this one. But and among all those kind of combinations, right, we get the minimum out of those all the combinations. Cool. So that's that. And okay, so how about a bottom up? I think, and it's always a good thing to practice both the top down and the bottom up, so you can get a deeper understanding of the DP. Okay. So, like I said, for the bottom up, you have to think it in a reversed way, right? Basically, from here onwards, you're getting from the current state, you need to move to the next state, right? But for the bottom up, with the current state, you need to think backwards. Basically, you have to think of, okay, what are the different like scenarios that can can get to the current state from the previous state. And that's the first difference. And second difference is the uh, how you do the for loop here, because and how you set up the base case, because for the top down, it's almost guaranteed that all the branches, they're all valid, except for the base case, because it's being controlled, right? Basically, you're from top down, you're starting from the valid state, and then you're just moving, trying to explore a more valid state based on the current valid state. Okay. But for the bottom up, not every combinations are valid, right? And because as you guys can see here from the top down here, right? So we are actually there are some cases that, I mean, it's not valid. So what are the invalid cases? The invalid cases are like maybe if we have three workers that have been marked to assign the bikes, okay? And but the mask here, let's say if the workers we're at 3 here. Let's see if three workers have been marked to the to be have a bike here. But what if the mask is 0, 0, 1, 1, 0, 0? What if there's only like two ones in this mask? So basically, no, this is an invalid state. It means that, okay, we're saying workers have been assigned to the mask, sorry, to assign to the bikes, but instead on the other side we only have two bikes being assigned, which is invalid state. But these things will not happen in the top down, because we're guaranteed here, right? Basically, since we're doing a top down here, the first state is always valid, which is 0, 0. Okay, and then from here onwards, right, we are exploring all the valid states, because it's guaranteed that, as you guys can see, we only assign an unassigned bike to the current person. So it's guaranteed that the state, uh, the index and the mask, they're always matched to each other. Okay, but if we're doing like the top down, sorry, the bottom up, since we are going to loop through all the possible like combinations, right? And some of them are invalid states, so we have to be careful about those. So and okay, and of course, so before doing that, the date and time complexity for this, right? So how many state we have here? We have like uh let's say we have the the worker and bike, right? So basically this one is like the workers times uh 2 to the power of bike. That's the total statement here. That's the total state here. And for each of the state, we'll be exploring all the bikes here. So it's going to be another B here, right? That's the length of the bike. So that's the total time complexity for this problem. Okay. And from here, actually, we can use this one to construct our bottom-up DP here. So we have we need these things here, right? So, and then we have a DP. So for DP, so what do we need? The DP, the first thing is that we have two dimensions. The first one is the worker. Second one is the 2 to the power of the B here. So which means when we construct the DP here, we have to do this, right? So the second dimension is what is this, right? So sorry, of this one, okay? Hmm? And 4 in range W plus 1, okay? Excuse me, what happened here? Okay, and here max size. What happened here? Okay. So the reason we are setting this one to max size is because we need to calculate the minimum value, right? So we initialize everything to the maximum. Okay. And then now it's the okay, you know what? Let's try to finish the our main for loop here. So on the outer loop here, we need to loop through the workers, right? Basically, we have a worker plus one, so which means we have worker equals to the workers I minus one, since we are doing like the one base and the worker is the zero base. Okay. Now the second loop is a mask. Okay. As you guys can see here, and so for the top down here, right? For the top down here, we are only exploring the valid uh, the valid states here. But here we are exploring all the mask, okay, in range like this, right? We're exploring all the masks for the current worker, but for some of them it's not valid, okay. So and yeah, same thing here, right? So with the current mask, how can we get to the previously state, right? Basically, same thing. We need to range the bike here again. Okay. So the way we are checking is that, I mean, if this range, if this one is one, then it means that okay, so so this one has been assigned to a bike, which means the previously state is so which means that the previously this bike has not been assigned, which means we can get to the current state from that state. Okay, so this is what I mean here. So basically, I do the check here, the k, right? Uh, and the mask heck is not equals to zero. So this means that this bike uh, has been assigned has been assigned, okay, to a worker, right? To a worker, okay. Yeah, then it means what? It means that okay, so let's do a get the distance for this bike first, right? So the bikes equals to this, the k, similar like the top-down version, and we have distance equals to get distance, right? The worker and the the bike, yeah. So now the only difference here is this, right? So we'll do a I mask, right? So which means that for the current bikes and the current mask, so we have find a way to get to the current state, right? So we do a minimum of that dp I mask of what comparing to what? So the previous state is that we have I minus one worker have been assigned to a bike and uh, and with this bike has not been assigned. Okay, so how can we do that? We just need to do a reverse. Basically, we need to remove this one from the current mask so that we can uh, convert it to the previously state of the mask, which we do a uh, one this k, right? We do a XOR of the mask. That's how we remove this one from this mask so that we can revert to a previously state here. And yeah, don't forget to add this distance. Okay. And then in the end, we do what? We simply return the minimum. We return the minimum of dp minus one. Okay, so why we do a minimum here? Uh, uh, because okay, so dp minus one means that okay, we have all the workers to be assigned to all the bikes, but the problem is that within all those kind of the possible values, right, of the mask here, we need to find the minimum out of them because let's say we have two workers and we have 10 bikes, right? So dp we have dp2 here and and the mask here, it could be anything. It could be 00110000, okay? And it could be DP 2, maybe 01000001. Basically, there are like multiple ways of assign this the bike to these two workers. That's why we have to do a minimum, out of all of them. Okay, but as you guys can see, right? So not all of the possible masks are valid. Only the ones with these two ones are valid. So how do we control that? So we control that. I mean, we control that by setting up like a base case. So the base case is this, like how we start from from the top down. Basically, the base case is we have zero workers and zero bikes. So which means this is a valid state. And with zero workers and zero spikes, the the total Manhattan distance is zero. Okay. And but to be careful here, I mean, someone I think it's tempting to do something like this. For example, let's say what if let's say the bikes is zero. Let's say sorry, let's see the worker is equal to zero, but the bike is not. Bike is not to zero. So which means we have zero workers, but we have like five bikes. I think it's tempting to do something like this. It means that uh with the mask, right, in in like something like this, right? So we do a DP like zero workers, right? Zero workers and the mask to zero. Similarly, as we can do something like this, uh, which is I equal in the workers, right? In range of W plus one. Okay. So this things means that okay, we have that we have this many workers, but we don't have any bikes, right? So something like this, because I mean, you might think that of course, with zero workers or zero bikes, of course the minimum distance is zero, okay, which is correct, but you cannot do this. The reason being is that not every state here is actually except for the 00, all the other state they are all invalid state. So right, because the problem is telling us each worker has to have one bike. But in this case, we have zero workers and we have many bikes here. So which means that uh, uh, mm, which means that not every worker can have a bike. Okay. Same thing for this one, right? Same thing for this. Like we have many workers, but we have zero bikes. Also means that okay, there's no basically not every worker can has like a bike. So which means we cannot set this to for loop here. The only thing we should set is 00, because with 00s, so that it's guaranteed that when we reach the last DP I here, all the other cases for the mask, they will all be max size. Only the ones starting from 00 will give us the correct answer. Okay. Yeah. Yeah. Okay. Let's try to run the code first. Yeah. Cool. So accept it. Submit. Yeah. As you guys can see here, right? Actually, this bottom up is actually slower than the top down. Why is that? Like I said, even though the time complexity is the same, but the difference that for the top down, we're only exploring the valid states, okay, by making sure each worker is assigned to a bike, and the mask matches with the current workers. But with the bottom up, as you guys can see, we have a nested for loop, three level nested for loop. Basically, we're looping through all the possible states. That's the difference. Okay. And cool. I think that's it for this problem. Yeah. And thank you so much for watching this video, guys. Stay tuned. See you guys soon. Bye bye.